Physics, Part 115. This equation is an expression for the pressure. This expression relates only to the x component of velocity of the molecules. For a molecule moving with the velocity c, an extension of Pythagoras' theorem, the three dimensions give the relation between c and the three components of velocity, cx and cy, cz and c square, to c square x to c square y plus c square y plus c square z. Because we are dealing with a large number of molecules in the random motion, the average value of the components in x direction will be the same as those in the y direction or the z direction. Therefore, taking the averages, the rotation means the average value or expression for the pressure can now be written. PV is equal to 1 over 3 nmc square. Since the average kinetic energy of a molecule is Ek is equal to 1 over 2 mc square. I beg your pardon, please. There seems to be a link between our kinetic theory equation for PV and energy. We can find this relation by rewriting the PV equation as PV is equal to 2 over 3 n. 1 over 2 mc square is equal to 2 by 3 NEK. We have already stated the ideal gas law in the forms of PV is equal to nRT is equal to nKT. Indeed, even real gases obey this law reasonably well under normal conditions. If our kinetic theory model and the subsequent theoretical derivation of the equation are correct, we can bring together the two equations for PV. This will allow us to relate the temperature of a gas to the average kinetic energy of its molecules. PV is equal to 2 over 3 NEK is equal to NKT, and E is equal to K is equal to 3 over 2 KT. This is an important result. We have obtained a relation between the average kinetic energy of a molecule in a gas and temperature of the gas. This will allow us to obtain an idea of the average speed of the molecules. Since Ek is equal to 1 over 2 mc square is equal to 3 by 2 kT. The quantity of the c square is called the root mean square speed or RMS speed of the molecules. It is not exactly equal to the average speed of the molecules, but is often taken as being so. The average speed is about 0.92 of the root mean square speed. The difference between the RMS speed and the average speed is highlighted in example 1 on page 152. Note that the RMS speed is proportional to the square root of the thermodynamic temperature of the gas and inversely proportional to the square root of the mass of the molecule. Thus, at a given temperature, less massive molecules move faster on average than more massive molecules for a given gas. The higher temperature, the faster molecules move. We've got a few examples here. The speed of 7 molecules in a gas are numerically equal to 2, 4, 6, 8, 10, 12, and 14 units. Find the numerical values of A, the mean speed, B, the mean speed squared C square, C, the mean square speed C square, D, the RMS speed. Example number 2. Find the total kinetic energy of the molecules in 1 mole of an ideal gas at standard temperature 273 K. We know that the average kinetic energy of one molecule is 3 by 2 kT for 1 mole of molecules, that is Na molecules. The energy is as explained.